Hi everyone, it's Mrs. H. Today we're going to talk about 10.3, which is about composition and inverse functions. We've seen some of this before, but this is just going to kind of take what we know and go one step further. So let's start out here. I gave you two functions. I gave you f of x and I gave you g of x. And what we're going to do is we're going to calculate some things with these. Remember that function notation means that we know that this passes our vertical line test. Every input has exactly one output. And remember our notation here for a question like number 1. F of 8 is just asking us to plug in x equals 8. So I'm going to do the square root of 2 times 8. That's going to be the square root of 16. Oh, and I know the square root of 16, that's 4. Notice that my answer is just 4 because the square root was already typed on the paper, and so it's only asking for that primary square root, that positive one. All right, now g, let's see. I want to plug in 3 into my g equation, and so I'm just going to do 3 plus 5. Oh, done. That one was quick. But the rest of these questions are a little different. F of g of 3. Well, this is a two-parter. You want to follow your order of operations, which means we're going to do our parentheses. And so we're going to do this inside piece first. So the first thing I'm going to do is g of 3. Oh, wait, we already did that in question number 2. The answer to g of 3 is 8. So now what I'm really asking you is, what is f of 8? We already did that because that was question number 1. So I actually don't have any more work to do. I can just say here my answer is 4. If I hadn't already done questions 1 and 2, it's the same process as questions 1 and 2. All right, let's think about something like g of f of 8. Okay, well this time I'm going in the other order. Inside first means f of 8 happens first. I know what f of 8 is. It's 4. And so my new question here is, what is g of 4? I'm going to plug in 4 to my g equation for x. So I get 4 plus 5. The answer to this question is 9. We can take this one step further, though. We can do this without knowing those numbers. So f of g of x. Well, what is g of x? G of x is x plus 5. And what do I want to do? I want to plug that into my f equation. That means in my f equation, anywhere I see an x, instead, I want to write x plus 5. Okay, well, I know how to simplify this a little bit. I maybe would think, can I do anything here? No, I don't think I know either of those square roots. Maybe I'll distribute, see if that gets me anything. No, it doesn't. So whatever, I'll just leave it like this, or this one here would be fine as well. We can go the other way around. G of f of x, again, you're going to work your inside out. So here, I want f of x first. Oh wait, I know f of x. That is the square root of 2x. And what do I want to do? I want g of that. All right, so I'm going to plug into my g equation. Everywhere that I see x, I'm going to plug in root 2x. So I have x plus 5. But instead of x, I'm going to write root 2x. Well, here I wrote the parentheses. They're not doing anything for me. So I'm going to just go ahead and have the square root of 2x plus 5. Done. That's my answer to number 6. What we just did on questions 5 and 6 is called composition of functions. Composition of functions is when you don't have a number like numbers 3 and 4, but instead you're composing basically a new function. I could call this one here on number 5 maybe h of x. I could call this one here on number 6 maybe m of x or something like that. I'm creating a new function by combining two other functions that I know in a very specific way. Let's take a look at a couple more problems here, and let's see what happens. Let's take a look at number 7 and 8 here, and then take a look closely at what's going on in them. First thing I'm going to do, I have two new functions, so let me pick two new colors here. I'm going to have f of x, and I'm going to have g of x. And then as I'm looking at these, I'm going to make sure I'm paying attention to my order. Let's see, number 7 wants me to do f of 1 first. Okay, I can do f of 1, that's no problem. F of 1 means that I'm going to plug in 1, so I have 3 times 1 plus 2. 3 plus 2 is going to give me 5. And what do I want to do is I want to do g of that answer. So g of 5. Okay, I can do that. 5 minus 2 over 3, that's going to give me 3 over 3. That's going to give me 1. That's my final answer here. All right, let's see, number 8. Let's try the other way around. Let's see, I'm going to do g of 3 first, right, because I'm working from the inside out. So let's plug in 3. I'm going to do g of 3 is 3 minus 2 over 3. And that's going to give me 1/3 as my answer. Whoops. Let me write it down underneath. That's going to give me 1/3 as my answer. And now I want to do f of that. So f of 1/3. All right, 3 times 1/3 plus 2. Well, 3 times 1/3 is 1. 1 plus 2 gives me 3. Take a look at these two questions. What happened in these two questions that you find interesting? What happened that you kind of wonder, did that mean to happen? I don't know. The biggest thing that I notice in these two is what I started with. I started with 1. I did something to it, and then I did something else to it, and I ended with 1. I started with 3. I did something to that, and then I did something else to that answer, and I ended with 3. So I plugged in 3, and I got 3 as my answer. I plugged in 1, and I got 1 as my answer. Let's try something else. I don't know. Is this going to work for everything? Does it matter if the G or the F comes first? Let's just try for every single X. If I can do this algebraically for every single X, then I can generalize. So let's do first f of g of x. G of x. Well, what is g of x? That is x minus 2 over 3. What do I want to do? Is I want to do f of that. Okay, so in my f equation, I'm going to do 3x plus 2, but instead of x, I am going to plug in x minus 2 over 3. Let's simplify here. 3 really is 3 over 1. I'm multiplying by a fraction over 3, so those 3's cancel. I get x minus 2 plus 2, and I get x as my answer. For number 11, other way around, I want f first. What is f? F is the equation 3x plus 2, and I want to find g of that. So I'm going to plug in that into my g equation. So I have x minus 2 all divided by 3. But what am I plugging in? I'm plugging in 3x plus 2. Well, here the parentheses aren't doing anything for me. They were just kind of helping me plug in, so I'm going to erase them. And I'll simplify the top. 3x plus 2 minus 2, those 2's are gone. So I get 3x over 3. What does that give me? That gives me just x. So both of these questions, what did I get? I got x in the end. I plugged in x. I did g to it. I took my answer. I plugged that answer into f. And I got my original x back. Likewise for number 11. This is the definition of an inverse function. So you want to use composition of functions to check for inverses. You must check both of these if you are answering the question, are these two functions inverses? Must check both f of g and g of f, and you better get x back in the end. Now, this isn't typed on the notes, but just a quick aside so that hopefully this makes sense to you. My favorite example of this is degrees Fahrenheit and degrees Celsius. So if I take some temperature, let's say we're measuring our temperature here in Acton, so we're measuring in Fahrenheit. And what do? I convert that temperature to Celsius with a formula, and then I send it to my friend, I don't know, in Canada, and then they send it to their friend who is in the US, and that person converts back to degrees Fahrenheit. Well, I hope the temperature stayed the same. I hope that it didn't change in the conversions, because then somebody's doing something wrong. It also works the other way. Let's say that my friend in Canada told me what the temperature was. I don't have any clue what that really means for me. So I convert it to Fahrenheit to figure out what it means. And then I tell my friend, oh, hey, the temperature that my friend up in Canada was this in Fahrenheit. And they say, I don't know what Fahrenheit is. I want to think about Celsius. They change it back to Celsius. Well, I hope the temperature didn't change, right? It makes sense that it shouldn't change. Let's take a look at our graphs from our last example, our f of x and our g of x. And let's look at how these two graphs are related to each other. F, pretty straightforward to graph. I have a y-intercept of 2. I have a slope of 3. So I'll go up 1, 2, 3. I'll go down 1, 2, 3. 1, 2, 3. I'll kind of cross over like that. This is my f graph. G, I'm going to have to do a little bit of work for G just to make it look nicer. What I'm going to do for G is I'm going to divide everything by 3. So I get x divided by 3 minus 2 divided by 3. If I want to think about slope, it might be a little nicer to say 1/3 x minus 2/3. And this is my G equation. Well, not great, but that's okay. My y-intercept here is going to be negative 2/3, and my slope is going to be 1/3. So let me think about what's going to happen. I'm going to go up 1 over 3, or I could go up 1/3 and over 1. I like that a little better because then I go up 1/3 and over 1, and now I have a nice point that I definitely can graph. Go down 1/3 and left 1. I have a second nice point that I can graph. Okay, this is much better. Let me connect. Now I don't have to worry as much about my fractions. All right, here is my graph for G. These two graphs are related. My slopes here, let's take a look. My slope, one of my slopes is 3, one of my slopes is 1/3. Okay, those are similar. They meet at a point. What point do they meet at? We could algebraically calculate that, but I think it's pretty clear that they intersect at the point -1, -1. What I want to point out to you is that these two graphs are symmetrical with each other. What is happening is these two graphs, if I were to take my coordinate plane here and fold it on that perfect diagonal line, what's the equation of that diagonal line? Well, that is the line y equals x. I would get the other graph. All of my ordered pairs are flip-flopped over that graph. Let's see. The pink graph, I had the point 0, 2. On the blue graph, one of those points that we came up with was 2, 0. Oh, hey, they meet at -1, -1. Those two are the same. Let's see another point on the pink graph, and let's see. This one over here is -2, -4. So if I think this is right, I think the point on the other side would be -4, -2. Let's see if that's on the graph. Oh, sure looks like it is. It's not perfect, right? Because I did not draw it perfectly, but it looks pretty darn close. This is really important about our inverse functions. Our inverse functions are reflected over that line y equals x. But the other thing is that your x and y values are all swapped, which of course they are, because what did I do? I flipped over this line where y equals x. So now all of a sudden on the pink, I flip-flop and y and x are switched. All right, let's talk about a few more things with these, and then we'll do plenty of practice with these as we go. So first thing, we're going to talk about our horizontal line test. I mentioned at the beginning our vertical line test, and our vertical line test is determining if something is a function. Our horizontal line test is telling us, is the inverse also a function? So if you think about this graph here for number 14, and you think about flipping this graph over that line y equals x. Let's see if I can do it. I'm not 100% sure I'll be able to. So here we are. I'm going to try to flip over that graph. Can I? Oh, I don't think I can. No, I'm not going to be able to. I know there are things that will be able to. I can't just rotate it. I've got to actually flip my paper over. So anyway, hopefully you can kind of imagine that. This curve here is going to flip up and be a curve like that. This part of my curve here is going to flip over and is going to kind of go like that. Now, what can you tell me about that new kind of flipped over graph? Well, it is definitely not a function. I know on this new graph that it's not a function because it doesn't pass the vertical line test. But what happened when I folded my paper over is the y-axis became the x-axis and vice versa. And so on my original graph, how I can check that without actually thinking about that drawing is I can draw a horizontal line. This intersects my graph in two places, which means that the inverse is not a function. All right, let's test B here. Okay, so B, is this a function? Well, yes, definitely, right? It passes the vertical line test. Is the inverse a function? Yeah, it looks like it. I will tell you right here in the middle, it sure looks like it kind of flattens off. It doesn't. It doesn't actually intersect with this line twice. It just kind of flattens off a little. So this one is a yes. That means we want to try to envision what our reflection would be. So here is my line that I'm reflecting over. Let's try to draw that inverse. This part, well, it kind of looks like it touches up there, and then I kind of swoop over until I get to 0. Okay, so that's pretty nice. And then if I fold, let's see, I'm right about there, and it looks like I've got to just kind of swoop down until I look like I touch the line again. So maybe about that for the green, for the inverse function. C definitely looks like it passes the vertical line test. Looks like it passes the horizontal line test. So let's draw that line that it's going to reflect over. It's my perfectly diagonal line. One nice thing about drawing your inverse is that wherever you touch that y equals x line, you still do. So I'm going to kind of swoop down and go up there. Oh, and then I'm just going to kind of keep going like that. Good enough. D definitely does not pass the horizontal line test. We still could find the inverse. The inverse would not be a function. All right, we have a few more. Let's talk about finding it algebraically. I think I'm going to skip graphing these if it's okay with you. You can go through and graph them if you'd like. Number 15, let's do that one. This one is a line, and I know that every line is going to pass the horizontal and vertical line test as long as it's not our horizontal or vertical line. And so I'm going to just find my inverse algebraically, and then you can graph them. This equation really, right, we've talked about f of x really kind of being like y equals 2x plus 1. And so what we're going to do for the inverse is we are going to, remember we're going over that line y equals x. We talked about our points flipping. We are going to flip our x and our y. So instead of y equals 2x plus 1, the inverse is going to be x equals 2y plus 1. Obviously, I don't like that equation, so I'm going to rewrite it. I'm going to do x minus 1 equals 2y. I'll divide, so I have x minus 1 divided by 2 is equal to y. And now let's talk about our notation. I don't really want both of these to be y equals and y equals, right? That's not super nice. I also want to show that this is the inverse of question number 15. And how we do that is with this f to the negative 1 notation. This means f inverse, and that's how we read it. F inverse of x. What is f inverse of x? That's kind of like saying y equals. Well, it's x minus 1 all over 2. There's our algebraic answer for number 15. You could also graph it, and you could see that they do reflect over that line, y equals x. One last one that I don't want to do, but I'm going to show you. Find the inverse and then prove that they're inverses. I like this question because this is kind of showing you two different ways. So first thing I'm going to do is I'm going to find the inverse. So I'm going to say x equals y minus 1 over 3. I'll multiply my 3 up. I'll add my 1, so I get 3x plus 1 is equal to y. So I'm going to call the inverse, they told me here to call it g of x. So I'm going to call g of x 3x plus 1. That's great to find it, but if you want to prove that they are inverses, what you have to show me is f of g of x and g of f of x, and that they both give you x in the end. Does it give you x? That's what you've got to show me. Does it give you x? If you have a problem and the first one you tried does not give you x back, you're done. They are not inverses. We'll do a bunch of problems like this. We've seen plenty of inverse functions without calling them that throughout the years, but this is going to be crucial to our next section. So come with questions. Let me know whatever questions you have. And yeah, all right. Thanks, everyone.